Imagine you're standing on a cricket pitch. The crowd is roaring, the sun is beating down, and at the other end of the field, a fast bowler begins his run up. A few seconds later, a small red ball leaves his hand at nearly 150 kilometers per hour and comes screaming toward your face. Now, here's the question: what exactly makes that ball dangerous? Is it its weight? After all, the ball weighs only about 160 grams. That's lighter than a large apple. Yet nobody would willingly let one hit them in the chest. So, what is the real source of its power? To answer that question, we need to understand one of the most important ideas in all of physics: momentum. Momentum is often described as mass in motion. Every moving object in the universe carries momentum. A drifting leaf has momentum. A speeding motorcycle has momentum. Even Earth itself, racing around the sun at nearly 30 kilometers every second, possesses an unimaginable amount of momentum. Physicists calculate it using a surprisingly simple equation. Momentum equals mass multiplied by velocity. And this equation reveals something fascinating. An object doesn't need to be extremely heavy to become dangerous. It only needs enough speed. Consider a cricket ball. Its mass is relatively small. But when that small mass is multiplied by a very large velocity, the result is substantial momentum. Suddenly, a harmless looking object transforms into a high-speed projectile. But there is another way to generate momentum. Imagine a massive truck moving slowly down a highway. Its speed may be low, yet its enormous mass gives it tremendous momentum. In physics, both speed and mass can contribute to the same outcome. And that creates a serious challenge, because momentum obeys one of the deepest laws in nature, the law of conservation of momentum. Momentum cannot simply disappear. Whenever a moving object stops, its momentum must be transferred somewhere else. There is no exception, no shortcut, no escape. And this brings us back to our cricket pitch. A wicketkeeper's job sounds simple: catch the ball. But from a physics perspective, something extraordinary is happening. The keeper must take a ball carrying significant momentum and reduce that momentum to zero. The question is, how can they do that without breaking their fingers? The answer lies in another powerful concept: impulse. Impulse measures how much momentum changes during an interaction, and it introduces a second equation: F equals delta P over delta T. Force equals the change in momentum divided by time. This equation contains a hidden secret. If the momentum change remains fixed, increasing the time reduces the force. And that's exactly what wicketkeepers do. Watch closely the next time you see a catch. Their gloves compress, their hands move backward. Everything is designed to extend the collision by just a fraction of a second. That tiny increase in time dramatically reduces the force experienced by their hands. The momentum still disappears, but it disappears more gently. The same physics protects your smartphone when it falls onto a soft carpet. The same physics explains why gymnasts land on thick mats. And it is the same principle that keeps millions of drivers alive every year. Imagine a car traveling down a road. The vehicle possesses momentum because of its mass and velocity. Now imagine it suddenly crashes into a wall. The car's momentum must drop to zero. If that happens almost instantly, the force becomes enormous, enough to cause catastrophic injuries. So engineers attack the problem mathematically. Modern cars contain airbags, they contain seat belts, they contain crumple zones. All of these technologies serve one purpose: increase the collision time. Airbags cushion the passenger, seat belts stretch slightly during impact, crumple zones collapse and absorb energy. Each feature extends the stopping process. Each feature reduces force. In other words, every modern safety system is an engineering solution to a simple algebra problem. And physics doesn't stop there. Let's return to cricket one final time, because batters use the exact same equation in reverse. When coaches tell players to follow through after striking the ball, they're not just teaching technique, they're teaching physics. A proper follow through keeps the bat in contact with the ball slightly longer. That extra contact time allows more momentum to be transferred. The ball leaves the bat faster, it travels farther, and sometimes it disappears into the stands for six. The same equation that helps a wicketkeeper survive a catch helps a batter launch a winning shot. That's the beauty of physics. The same law can protect you or empower you, depending on how you use it. And once you begin noticing momentum, you see it everywhere. In sports, in car crashes, in rocket launches, in industrial machinery, Even on mountain highways, where runaway truck ramps use long gravel beds to slowly absorb the momentum of heavy vehicles before disaster strikes. The details may change, the objects may change, but the rule remains the same. Momentum can never be destroyed, only transferred. And by understanding the relationship between mass, velocity, force, and time, humanity has learned how to work with one of nature's most unstoppable quantities. Because in the end, momentum isn't just a physics formula, it's the invisible currency governing every collision, every catch, every crash, and every movement in the universe.